Okay, the last thing we want to look at here with these trig equations is actually an application of trig equations, specifically trig equations involving the sine function. Everybody's probably experienced this at one time or another, where you were maybe at a public pole or an in-ground pole, and you were standing up on the side, and uh, down in the pole was some object, right? And if you tried to uh, jump right to where it looked like that object was, you would actually not be finding that object. Or maybe you've done this where you've stuck uh, a cleaning tool, trying to take leaves or something out of the pole, and once you hit the uh, water level, something strange happens to your pole, right? It literally looks like it bends. Right? It literally looks like it bends. Uh, So everybody's kind of seen that, hopefully, at some point before. And actually, what governs that behavior is a result known as Snell's Law of Refraction, which was actually an idea that was discovered a long, long time ago uh, by the ancient Greeks. They had a knowledge of this, uh, how things would be refracted, how things would bend. Okay. And so that's what we want to take a look at now is this idea. Uh, so let me just get rid of that stuff. And let me show you what the actual role is for Snell's law. Because what it actually has to do with is how quickly light moves through uh, the medium. In this case, the example I'm looking at, we're going from water or from air to water. Uh, so light moves through uh, air at a different rate than it moves through water. Uh, you would also see something like this if you were ever someplace that had a really thick glass window, a couple inches thick. You would see the light bending as well. Maybe you've dealt with a prism, light coming through a prism, how the light bends as well, different things like that. So here's what Snell's law says. Here's what Snell's law says. And we draw a little coordinate axis here to make this visual. Uh, so light is passing through one medium with a velocity of v1. And what happens is the light comes through, is passing through uh, the perpendicular with some angle theta 1. Okay. That first angle has a name. That's called the angle of incidence. And then what happens as you pass into a new medium, the angle, depending on the second medium, how fast the light passes through it, uh, light beam is either going to bend towards or away from the perpendicular. Okay. Now it turns out if the object that you're coming into has a slower velocity, then it's going to bend towards it. If it has a higher velocity, it'll bend away from it. And that's called the angle of refraction, the second angle. And it turns out, quite remarkable, this behavior that we're going to have here, that the sine of theta 1 divided by the sine of theta 2 is actually equal to the velocity in the first medium over the velocity in the second medium. Okay. And this is known as Snell's Law of Refraction. And so that V1, velocity of 1 over velocity 2, is known as the index of refraction. Is known as the index of refraction. Okay. And so again, the idea here is if V2 is smaller than V1, then again, what's going to happen as you go in is the angle is going to bend towards it. It's going to bend towards the perpendicular. So in our example here, the problems we're going to be dealing with, we're actually usually given the index of, we're usually given this index of refraction and just asked to use it. So in our example here, we're told that the index of refraction for light in a vacuum, now that's a little bit different than light in our atmosphere. To light in water is 1.33. So again, if you were doing light in the atmosphere to light in water, then the index would be slightly different. Light moves through our atmosphere slightly slower than it moves through a vacuum. So if the angle of incidence is 40 degrees, we want to find the angle of refraction. Okay, so let's tackle this problem here. So we would begin with this relationship, sine of theta 1 over sine theta 2 is equal to our index of refraction, right? That's what we just saw up above. Sine theta 1 over sine theta 2 equals V1 over V2. And then I told you that V1 over V2 is called the index of refraction. So what else do we know here? Well, we know the angle coming in is 40 degrees. So sine of 40 degrees over sine theta 2 is equal to 1.33, right, from which we can solve for theta 2. So we just flip-flop the sine theta 2 and the 1.33. Get sine theta 2 equals sine 40 divided by 1.33. And then this becomes a calculator problem. We make sure here again we're in degree mode for this because they want angles in degrees here. We just do the inverse sine of the sine of 40 divided by 1.33. And that gives me a mixed number. Let me fix that. 28.9, let's say, rounding off. So theta 2 is 28.9 degrees. And so you can see, again, this idea of it being bent. This idea of it now being bent away from you. Or bent towards the middle, as I mentioned here, if it's going through something slower. Okay? And so that's Snell's Law of Refraction.